Here's Precal lecture 11.2.2. It's operations with complex numbers geometrically. So it says you know how to add, subtract, and multiply complex numbers, and now how to represent complex numbers in the complex plane. Can these operations be represented in the complex plane? You will explore this idea as you work through today's lesson. So it's got geometric addition and subtraction of complex numbers. So they give you a vector. Oh, I keep saying vector. You can represent them as vectors. They give you the complex number z and w. So evaluate z plus w. So all I would have to do is just add a z and w. So I'll add the real parts and I get 5, and I add the imaginary parts and I get 1. So that's easy enough. On one set of complex axes, graph z, w, and z plus w as vectors. So these three things right here. How are z and w related to z plus w graphically? So I think I put z went right 2 and down 3, so that one right there is z, and then w went right 3 up 4, so there's z, and there's w, and then z plus w. Well, we just added it algebraically, and we found out it was 5 plus I. So that went right 5 up 1. So I think I remember something about when we were learning about vectors, but it turns out if you make a parallelogram with z and w, like if you complete it to make a parallelogram, the z plus w ends up, it doesn't really look like it, but it ends up being the diagonal. Okay, and then if we evaluate z minus w, it would be the z minus w. So 2 minus 3 is -1, and negative 3i minus 4i is -7i. And on another set of complex axes, how about if we autofocus this? On another set of complex axes, graph z, w, and z minus w. Oh, I'm not sure if I did those. How are z and w related to z minus w graphically? Well, it turns, I didn't do those ones. It turns out that z minus w is the diagonal of the parallelogram. So kind of just in the same way, because really you're still adding it's z plus negative w, so it's still going to work out that way. 1196, geometric multiplication with complex numbers. So we've got u, they want 3 times u, so we already know this because a lot of these things we can just kind of relate it to what we've learned about some vectors and things. So you just scale it up, so 15 and -12, and then on one set of complex axes, graph u and 3u, and I think as vectors. So how are u and 3u related graphically? So 3u is just going to be, it's going to have like the same direction, but the magnitude would be 3 times bigger, so it'll just go longer, 3 times longer in the same direction. What are the moduli and arguments of u and 3u? So remember, moduli it's kind of the same thing as the hypotenuse of a triangle if you were to draw a triangle using the positive x-axis as the base, but also it's kind of like the magnitude of a vector. So the moduli and argument of u and 3u. So u would be, where's u? I think I have this written somewhere else. well, okay, where's u? So the moduli of u, you would just go, oh, I wrote it right here. So you just use Pythagorean theorem, because this side is 5. Like if you did draw a triangle out of it, we got 5. It's Pythagorean theorem, 5 squared plus 4 squared. So it ends up being square root 41. And then what's the argument of it? Well, you would want to, you can do inverse tangent on there. So for u, it goes right 5 and down 4. Is this u? 5 down 4. So that's 4, that's 5. You can use, this will be the argument. Oh, remember the argument is the direction. So we can find out what that number is and then subtract from 360, or we can just say the negative of that number. So this would be tangent, because tangent is opposite over adjacent, like SOHCAHTOA. So this will be inverse tangent of 4/5. And inverse tangent of 4/5 ends up being inverse tangent 38.65, well, we'll say 38.66. That's just if we were looking at a triangle, but really it's negative 38.66 because we're going down, we're going clockwise from this positive x-axis. So I think they've got that there. And then if I did the same thing for 3u, I'm still going to have the same angle because it's got like a slope. It's got the line, the vector has the same slope, so it's still going to have the same angle. Oh yeah, and the magnitude of the vector is going to be 3 times longer, so it's 3 times the modulus there. Letter D, imaginary multiplication. Evaluate I times u. So I think this one is a little interesting. So if I want to go I times u, that would be 5i minus 4i squared. Oh, I did it right here. So I squared is negative 1. So now I got 4 plus 5i. There it is. And I think it moves it like rotates it. Yeah, it rotates it 90 degrees counterclockwise. Because see, now we're at right 4 up 5. 1, 2, 3, 4. This is supposed to be a 90 degree angle. See how it changes it a little bit. It rotates it. And then letter F says, what are the moduli and arguments of u and I times u? So I think we already talked about u, and it was square root 41. And then I times u is going to be the same because it just got, see how it just got like, it's kind of like a rigid transformation. It got rotated. Arg u, the argument of u, remember it was negative 38.66. The argument of I times u is, I think I did it right here. Oh, here's my diagram. So if that's u and that's I times u, this one goes right 4 up 5. So this is tangent is opposite over adjacent, so it's 5 over 4. So that's actually how I got that number. Okay, so that was 11-96. Yep, I think I have to make another video for the next 2 problems.